Hello everybody, thank you for tuning in. We're going to go over section 4.2 in the textbook, which is entitled Null Spaces, Column Spaces, and Linear Transformations. Much of this section is going to be a reiteration of some terminology that we've already learned, some new ways to look at null spaces, column spaces, and linear transformations now that we have discussed vector spaces. Okay, so we can still talk about the null space and the column space as a subspace now of a vector space, namely Rn. Okay, and first thing we're going to do is talk about the null space. Okay, then so same definition as before. The null space of an M by N matrix A, written null A, is the set of all solutions to the homogeneous equation AX equals 0. And we can now write that in set notation as well. Null A equals the set of all vectors X and Rn, so that AX equals 0. So let's do an example. Okay, our first example here is we're going to be looking for a matrix C such that Z equals null C, where Z is the set of the column vectors with entries B minus 2A, A, and B, where A and B can be any real number. Okay, so we want to find some matrix so that this set Z ends up being the null space of that matrix. The way that we're going to accomplish this is I'm going to take my set Z and do a rewriting slightly of this set. So Z, so Z is the set of all matrices B minus A, B, such that I had to rewrite that. Z is the set of all matrices where the first entry is B minus 2A, the second entry is A, and the third entry is B, and AB can be any real numbers in R. First thing I'm going to do to help us write this as the null space of a matrix is I'm going to do a rewriting of this set. Okay, so I'm going to write this as the set of all vectors x sub 1, x sub 2, x sub 3, such that, now notice if you look at the first way I wrote this set Z, the first entry is the third entry minus twice the middle entry. Okay, so what I can say here is our first entry x sub 1 is equal to the third entry minus twice the second entry. Okay. And of course, x sub 2 and x sub 3 are going to be real numbers. And I'm going to rewrite this set one more time. This is a set of all vectors x sub 1, x sub 2, x sub 3, such that x sub 1 plus 2x sub 2 minus x sub 3 equals 0. So the condition on my column vector is a single system of equations, okay, in three variables, x sub 1, x sub 2, and x sub 3. Now, there's several matrices that I could construct that would give this set as a null space, but the only real condition is since there's three variables, right? This is a subspace of R3, right? Every vector in this set has 3 rows. So whatever matrix I construct is going to have 3 columns to be able to multiply by this vector and end up getting the 0 vector. Now I said this matrix, since the vectors in the set Z have 3 entries, the matrix A, to multiply by these vectors, must have 3 columns. Since there is just one single equation involving those vectors, we can just use a matrix with a single row and 3 columns. And the coefficients If you look at the expression x sub 1 plus 2x sub 2 minus x sub 3 equals 0, okay, the coefficients on x sub 1, x sub 2, and x sub 3, those are going to be my entries in each column in my 1 by 3 matrix. Okay, so to make more space, I had to rewrite our set Z, since we've rewritten it now. And what we're going to do is we're going to define the matrix C. Okay, there's a single equation here, right? This is a system of one equation and three unknowns. So C is going to be a 1 by 3 matrix with entries 1, that's the coefficient on x sub 1, 2, that's the coefficient on x sub 2, and minus 1. Okay, so there's my matrix C. It's a 1 by 3 matrix. And then just to verify that the way that Z was originally defined as vectors of the form B minus 2A, A, and then the third entry being B, where A and B are any real number, just to verify that that all of these vectors are really in the null space of the matrix C that I've just defined. If you multiply this out, okay, this is a 1 by 3 matrix times a 3 by 1 matrix, so the result of multiplying these matrices is it's just going to be a 1 by 1 real number, and we'll multiply this out. I'm going to take 1 times B minus 2A, okay, so I just did the multiplication of 1 with B minus 2A. Okay. Now I'm going to multiply 2 by A. Okay. So now we end up with a plus 2A. And finally, if you take negative 1 times B, okay, the last result would be minus B on the right. And sure enough, the minus 2A plus 2A will add to 0, and the B minus B will add to 0. Okay, so we could actually verify. We could start with this matrix C. We could form the augmented matrix for the homogeneous system, and we could reduce that to a system of equations that's going to be equivalent to the system that's given by this set Z that I rewrote up here. Okay, so anything in my set Z, I multiply it by this matrix C on the left, we get the 0 vector, so that does confirm that the null space of the matrix C would be the set that we were given originally. Now, a theorem from a previous section, theorem 2, the null space of an m by n matrix A is a subspace of Rn. So the number of columns of A are going to determine what your null space is a subspace of. And equivalently, you could also phrase this as the set of all solutions to a system AX equals 0 of m homogeneous linear equations, so you'd have m rows in the matrix, and n unknowns, that tells you have n columns in the matrix, forms a subspace of Rn. Okay, so another thing we could do is look at another example, such as, is the set Z of all column vectors with 4 rows, A, B, C, D, such that, and these are real number entries, such that 5A minus 2B plus 4C equals D, and 4B minus 2C equals A, and I want to know if this is a subspace of R4. So the first thing here to notice is, again, I can kind of mess with this set just a little bit. In that first expression I can subtract D to the left, and in the second expression I can subtract A to the left. And I could rewrite the set Z as a set of all vectors A, B, C, D, such that 5A minus 5a minus 2b plus 4c minus d equals 0, and 4b minus 2c minus a equals 0. And in rewriting the set z in this manner tells me that z is really just the set of all solutions to a homogeneous system of two equations and four unknowns. And by the previous theorem above, that would tell me right away that Z is a subspace of R4. Again, the way that I've written this now, the two conditions on this set, again, those are that's a system of two homogeneous equations and four unknowns, and since Z is the set of all solutions to that homogeneous system, that right away tells me that Z is a subspace of R4 without even having to go and verify the three original conditions of a subspace, namely that the subspace contains a zero vector, a subspace contains any sum of any vectors in that subspace, and also that the subspace is closed under scalar multiplication. So what that means is, right, you take any vector in the subspace, you multiply it by a scalar, and you again get, your result would again be a vector in the subspace. Okay, so theorem 2 allows you to look at particular sets of column vectors, and if the conditions on that set of column vectors are just a system of homogeneous equations, then that right away tells you have a subspace. Okay, so on to the column space, and again, same definition as before. The column space of an M by N matrix A, written as col A, that's a set of all linear combinations of the columns of A. And we've seen this before. If A is written in the form A sub 1, A sub 2, again, those are representing the columns of A, then we can write col A as the span of those columns. Okay, remember, the span of a set of vectors is the set of all linear combinations of those vectors. Okay, so example 2 is similar to the previous example. I should really be calling this example 3. Okay, we're going to find a matrix A so that W equals col A, where the set W is defined to be the set of vectors of the form B minus A in the first row, 2A plus 3B in the second entry, and minus 4B in the third entry. And this it's a set of all vectors of that form where A and B are any real number. Now this is a lot less work than trying to find a matrix so that the given set is the null space of that matrix. So we don't really have to work as hard here. Essentially what we're going to do is we're going to take the general form of a vector in W, we're going to decompose it into a linear combination of column vectors, and those column vectors are going to form our matrix A. So again, I write down here a general vector in W, okay, and this can be decomposed now, just like when we're finding the parametric vector form of the solution set to homogeneous systems of equations. Each single row has a coefficient of A and a coefficient of B. So this can be rewritten as A times a column vector, where you're looking in each row for the coefficients of A. In the first row, the coefficient of A is -1. The second row, the coefficient of A is +2. And in the third row, the coefficient of A is 0. And then it's going to be plus B times the column vector 1, 3, and -4. So those were the coefficients of B in each row. Now if I define my matrix A, so let's let A just be the matrix given by those columns, then that's going to imply that W is equal to col A. Okay. So essentially the set W is spanned, since W can be written as a linear combination, any vector in W can be written as a linear combination of the vector -1, 2, 0 and 1, 3, -4. That means those two vectors are going to span W, i.e. if we put those vectors in a matrix, if we use those vectors as columns in a matrix A, those columns are going to span W, and therefore W is equal to col A. And then we know another way to write this is we could also write that this is the span of those two vectors, -1, 2, 0, and 1, 3, -4. Okay, and then last on our list here is to, again, talk about linear transformations. Okay, now, before, our linear transformations, before we were really only working with Rn, so we were just working with, n-dimensional space. So we had linear transformations from, say, Rm to Rn. Okay, now, more generally, you can actually define a linear transformation from any vector space. So our vector spaces now are, really our vector spaces are just like most of the ones that we've seen have been subspaces of Rn or Rm. So in class, we did look at a few other interesting vector spaces, like we looked at the vector spaces of all polynomials of degree at most n. Okay, and then there was also other vector spaces like the vector space of continuous functions on a particular closed interval. Okay, so now instead of just having linear transformations from Rm to Rn, we now are just going to have linear transformations from any general vector space to another general vector space. So the definition again is similar as before. Linear transformation T from a vector space V into a vector space W. Let me do a little finagling there and increase the size. Okay, so again, a linear transformation T from a vector space V into a vector space W is a rule that assigns each vector x and v a unique vector T of x and W, and it's the same properties as before. T of u plus v is just T of u plus T of v, so the transformation has to basically distribute over vector sums. And then if you do the transformation of a scalar times a vector, that scalar can pass through the capital T. So T of Cu would be C times T of u for all u in the domain, essentially the vector space V, and all scalars C. And two new definitions, and we've talked about the range before. The range is essentially the set of all images. Right, so the range of T is the set of all vectors T of x, where x is in the domain, which is the vector space V. And interestingly, the kernel, and actually I should really add a piece here because, well, just take a look at this for a second. The kernel of T is the set of all vectors U and V that get mapped to the 0 vector. So oftentimes you will also see the kernel referred to as the null space of the linear transformation. So, if you have a linear transformation from Rm to Rn, and you look at the kernel of the linear transformation that's given, or well, the linear transformation using you're going to have a standard matrix, right? So the So if you had a linear transformation T from Rm into Rn, you're going to have a standard matrix A, and remember, your linear transformation is given by that standard matrix, and the null space of that matrix then in that sense is going to be exactly the same thing as the null space or kernel of the linear transformation. It's just that these definitions are much more general. Again, the vector spaces V and W can be they can be Rn or Rm themselves. They can be subspaces of Rn or Rm, and even more generally, they could be the set of all polynomials of degree at most n, the set of all. We're going to see the set of all functions that are differentiable and have continuous derivatives is also a vector space. And same with the set of all continuous functions on a particular closed interval. So again, the main idea of this section is to take definitions that we have seen before in terms of Rn or Rm, and then now just extending them to be applicable to any general vector space V and W. Okay, and then another fact that I should share here is that if you wanted to show that something was a linear transformation, remember you have that starred property that says that to show T is a linear, let's respell that, to show that T is a linear transformation, it's to show that T is a linear transformation, it's enough to show that T takes a linear combination of two vectors cu plus dv and has image ct of u plus dt of v. Okay, so that would be sufficient to show that something's a linear transformation. So last example for the video. So what we're going to do is we're going to define a transformation capital D from a vector space V to W. V is going to be the vector space of all real-valued differentiable functions whose derivatives are continuous on an interval from A to B, also differentiable on that interval from A to B, and let W be the vector space of all continuous functions on the closed interval from A to B. And this transformation D from V to W is going to be the differentiation transformation. So i.e., that means that D of some function f, its output is just going to be f prime the derivative. Okay, so finally bringing in some calculus into linear algebra. So we've been waiting so long for it, and it's finally here. So for step one, to show if the transformation is linear, what we need to do is we need to apply the differentiation transformation to a linear combination of two functions f and g. So I can do d of c f plus dg. Okay, so f and g are functions that are differentiable on a closed interval and also have continuous derivatives on that closed interval. Now, by definition, d is going to take cf plus dg, okay, and write cf plus, we'll just put the prime on the outside. Okay. So it's going to take it to the derivative of cf plus dg. However, one thing we know from calculus is that, first of all, the derivative of a sum is the sum of the derivatives, and we also know that the derivative of a scalar times a function is the scalar times the derivative, so it should be no surprise that this does equal cf prime plus dg prime. Okay, and that is equal to c capital D of f plus d capital D of g. Okay, and I'm screwing up my video here. So let me pause and rewrite this for a second with some more space. So yeah, in that last step again, we knew that the derivative of CF plus DG is CF prime plus DG prime. Okay, so again, the derivative of a sum is the sum of the derivatives, and the derivative of a scalar multiple of a function is the scalar multiple times the derivative, right? Essentially, the scalar can be pulled in front of the d over dx if I was writing it in Leibniz notation. Okay, but writing CF prime plus DG prime back in terms of the linear transformation, that's C d of f plus the scalar d times capital D of g, and that implies that d is linear. Okay, so that is a linear transformation. Okay, and then question. Okay. So again, what we're going to do is we're doing part 2. We're assuming that we have a function f that's in the kernel of d. So d of f, which is equal to f prime, is going to be equal to the 0 function. And we know from a calculus theorem that this implies that, well, if the derivative is 0, that means that f has to be a constant function on the interval AB. Okay. So that just tells me that the kernel of D is a subset of all constant functions on the closed interval from A to B. Okay, and you'd also have to make the argument that if you start with a constant function, its derivative would be 0, i.e. it's in the kernel of the linear transformation D. So now if f is constant, okay, that's going to tell you that d of f is equal to 0. That implies that f is in the kernel of D. Okay, and basically what I just showed that I showed the kernel is a subset of constant functions on AB, and then I showed that the set of constant functions is a subset of the kernel of D, and then that would tell me that the kernel of D is the set of all constant valued functions on the closed set AB. Okay, so if I give myself here a new white page. So for number 2, what I can say then is that the kernel of D is the set of all functions f on the interval AB such that f is a constant. Okay. So that takes care of the kernel. Now we're going to look at what the range of D is. Okay, now the codomain is the set W. It's all continuous functions on AB. So start by letting f be in the range of D. Okay, then what that means or implies is there is a differentiable function. So there exists a capital F in V. Okay, so there's a differentiable function whose derivative is continuous. Okay. So there's an F in V so that d of capital F equals lowercase f. Okay, i.e. what that means is that f prime has to equal f. So remember, if f is in the range, that means there's some differentiable function with continuous derivative that maps to f. Okay. Okay, so f prime equals f. Now, since f is in v, it's differentiable and has a continuous derivative. So this implies that f is continuous. Okay, and I guess that was already something we knew anyways, because the codomain of this linear transformation is the set of all continuous functions on AB. Now, my claim here is that the range of D is just going to be the codomain. It's going to be the set of all continuous functions on AB. So, suppose, for the other direction now, suppose f is continuous on the closed interval from A to B. Okay. Now, from Calculus 1, there's a theorem that says any function that's continuous on a closed any function that's continuous on a closed interval has to be integrable. Therefore, it has to have an antiderivative. So, what this implies is there is a function capital F, which is the antiderivative, so that f prime equals f. Okay, and that implies that d of f equals lowercase f, which means that f is in the range of D. Okay, so what I just showed was if f is in the range of D, it's got to be continuous, and if I start by assuming it's continuous, it has to be in the range of D. So that implies the range of D is, and I'm going to write it this way. This is notation for the set of all continuous functions on the closed interval from A to B. Okay, so a little sloppy of a video, not my best stuff, but what we're going to be doing in class on Monday is I'm going to make a worksheet, and maybe we're going to be going over some homework problems. So I'll basically be having everybody working in class for maybe 30-35 minutes, and then we'll wrap up the last 15-20 minutes with a discussion going over the problems. But anyways, thank you for watching. Once again, sorry for being sloppy in a couple spots, but everybody have a good weekend, and I'll see everybody on Monday.